Okay, in this video we're going to start to develop a little bit more sophisticated techniques to evaluate limits, and we're going to study the direct substitution technique. And this is really, out of all of them, I think the easiest, because literally you substitute the value that you're approaching into the function. So before we get going on this example, let's go to the graph. To get an idea of what we think the limit might be. This is a good review of the graphing technique. Here's one right here. Here's my curve. And as we let our x value approach 1 from the left-hand side, you can just kind of see where your red ball is approaching. And it looks like it's approaching 3. Okay, as I jump to the other side, of 1 and let x approach 1 from the right hand side, okay, it looks like we're also approaching 3, but this time from the top direction. I could go and plug this function into my calculator and plug in values that get really close to 1 and show that those values are getting really close to 3. Your y values would be getting really close to 3. If you don't know how to do that, I show a couple of examples in the previous videos how to do that, so you can go back and look at those if you need to. Okay, so one thing you'll notice, actually let's go back to here. One thing you'll notice is that if you take your function and just say, well, what is 1? Where does 1 actually get sent to? And 1 actually gets sent right here to 3. Okay, so it makes sense then if I just take the thing that I'm approaching and plug it directly into my function, I should get my limit. Okay, so in this case I'm just going to substitute a 1 in for wherever I see an x, and I'm just going to use a different color here to show my substitution. Okay, so 1 squared is 1, plus 1 is 2, plus another 1 is 3. So just using direct substitution, I evaluated this limit without looking at a graph, without looking at a table. I think the graph and the table are a little bit more intuitive, but this is certainly quicker to do it this way. Okay, well, the next example, if upon first inspection, if we just try our direct substitution technique, you'll notice that we get a 0 in the denominator. Okay, so what does that mean? Does that mean our limit doesn't exist? Or does it mean something else? Well, let's, as usual, when in doubt, go to the graph. And I have the graph here. And let me get this down just a little bit. There we go. Okay, so here's my function. And here's my parabola. Okay, now this parabola looks strangely familiar. In fact, if we compare it to our previous parabola, they look pretty close to the same. Okay, a little bit different scale. That's why it looked like it maybe changed a little bit. But you can see that this parabola is slightly different in the sense that it has a hole right here. Okay, so this function 1 is not in the domain, which is why we get this hole. Okay, so if we imagine x getting really close to 1 from the left-hand side, it looks like my function is getting really close to 3. Okay, in fact, if we approach 1 from the right-hand side, it looks like we get really close to 3 from up above. The only problem with this, though, is we just can't take 1 and plug him into this. Okay, so life would be really good if we could find another function that was exactly like this function, that agreed with this function everywhere except maybe possibly at this point right here. And it just so happens that I chose a nice function, and if you recognize this is just the difference of two perfect cubes, and if you remember how to factor that, it factors accordingly. Okay, it factors into the product of a binomial times a trinomial. I think that's right. And this is all over x minus 1. Okay, so all I've done here is I've taken this guy and I have turned him into this. I guess what I should have done is put a limit statement right here. The limit of that is x approaches 1. I don't want you to think that this is somehow the limit of this thing. So here we have this new limit. It's the same exact function. I haven't done anything but just kind of changed its close a little bit. It's the same thing, it just looks slightly different. Okay, so one thing you'll notice is we have an x minus 1 in the denominator, an x minus 1 in the numerator, and these guys reduce. Okay, it reduces so that really my new limit is the limit as x goes to 1 of x squared plus x plus 1. Well, we've already done this. Okay, we did it up here, and up here we used direct substitution. So no sense in rewriting our work that we did up here. We could just look up here and see that this limit equals 3 as well. Okay, so again, looking at the graph, pretty clear that as x approaches 1 from the left and 1 from the right, we're clearly going to 3. Okay, the only difference between this function and this function is this function was defined at 1 and this function was not. Okay, so that's a introduction to the direct substitution technique. In the next couple of videos I'm going to be showing really some more techniques so that we can actually use direct substitution to our advantage. We'll see you then.